Hello, welcome. We're going to go over this problem today. Suggest friends by using the umpire method to solve this problem. So let's go over the problem statement. So imagine if you were building a social network from scratch, a private social network for your school. You know that all the students are in clubs and things that generally create communities already, but that sometimes those communities don't share all the contact information. You want to build a friendship suggester so that people who are already in the same social clubs can become friends. So you have a social graph already tracking friends. Here's an example graph. So we have an example graph. We have Alice, Bob, Carol, Dave, Eve, Faith, and Grace as nodes. And we also have another friend group two. So that's friend group one. Friend group two is Zed, Xavier, Quill, and Robert. Friend group three is Heidi, Naj, Ivan, and Trent. And we have the friend graph edges, which relate all the friends in group one, group two, and group three. And then this is how you visualize it. This is the friend graph for group one and group two and group three. And then you want to create a method for which a graph called suggest friends can take and users name suggest friends for them based on who is friends with people who you are already friends with. So return a set that suggests all friends the highest count of common friendships. So for graph one, if you choose Faith to be the one that we suggest friends to, then we get the most common friends are uh, the highest count of common friendships are Alice and Bob, and so we output Alice and Bob. And for graph number two, we pick Robert to be the guy that we suggest friends to, and he's friends with Xavier and Quill, and so that the most common um the suggestive of friends, the highest count of common friends is Z. So Z is suggested here. And then for graph for suggest friends for Ivan, everyone's connected, so there's no one to suggest, so we output the set. So now that we have an understanding of this problem, we can go and start uh, uh, let's write down an understanding first, actually. So we know what the input and outputs are. So the input is a graph, a social graph, and me and a friend. Um, and then we want to output um, friends, suggested friends with largest number of um, common friendships. Okay, so now let's match this problem. So this is similar to um, uh, other graph problems. Um, we're going to use sets and lists. So that's other it's similar to other problems with these kinds of elements. And then we can plan for this. We're just going to um, initialize um, my friends list and and potentials. And then we're going to find for loop over friends list, and then loop over potential friends list. Um, then um, add a friendship score, And then if potentials then we want to add potential friends. And then we want to get friend counts. And then we want to get best friend counts. And then we want to output set best friends. Okay, so let's implement this plan. So we first have my friends equals sets of members. And then we have potentials equals sets. And then we have for friend and my friends, for potential friends, friend and sub that members, friend and potential friend, not in my friends, with potential friend. Not me. We want a friendship score, which is friendship score, which is set self dots members potential friend. Cut into section my friends. And then the potentials dot get friendships for potentials friendship add friendship friend. And then else potentials friendships equals potential. And then, oh, damn it. So, I just, um, went backwards here. So I actually have it set up here. So let me just finish what I ended on. So I ended on potential friendship score equals potential friend. And then I have friend counts equals list potential select keys, and then friend counts that append 0, and best count equals max friend counts, and return potentials that get best count set. So let's just um, code check this. So we have passed all tests. So let's just step through the review of this problem. Okay, so our review of this problem, we have this problem. We're going to first initialize all the members. So we have all the nodes. And then we have all the friends, and then we go through suggest friends, and we just add potential friends and add to the potential friend score. And we continue on going through the potential friends and potential friend scores, and until we have a friendship score of 2 for the best count, and we have the friends in the best count of 2 friendship scores, and we have Heidi as the friend there. So now that we're finished with this review, we can go and evaluate this problem. So this problem, so the evaluation of this problem is an O(n) squared time complexity problem, and an O in space complexity. So we use O(n) space because we use potentials as friends set and my friend set members. And you have O(n) squared time complexity because we go through these 2 for loops here and evaluate potential friends. So that's the cap for this problem. So thanks for listening.